So all you've got to know is the formula. All right, but here's kind of what they did real quick in your book, just to make sure we're clear. Do we understand if I wanted this arc length? All right, so what I really wanted was like if an ant crawled around that curve, how far is that ant gone? But I could estimate it by finding like segments. And then doing what with those segment lengths. So if I measured from like here to here, if I wanted the measurement from that all the way to that, what I could do to get an estimation is measure straight from here to here, and then measure straight from there to there, and then measure straight from there to there, and then do what with those three segment lengths? Add them up. Well, how do you find a segment length? I mean, that's basically, 8th grade math. Don't you use that distance formula? So that distance formula was the difference in your x's plus the difference in your y's. Okay, so that's just your distance formula from like 8th grade math. All right, so instead of putting like, these are gonna, then I gotta do, that's the distance between these 2 points. Then I'd move to do the distance between those 2 points and so forth. So all I did was just change x, one x minus the other x to delta x. So I'm gonna find the change in x between 2 points and the change in y between 2 points. I'm gonna square those and take the square root, and that'll get me the distance between these 2 points. So I'm gonna do that for several of those lengths. Now, here's kind of the trick that the book does, but it kind of doesn't, sometimes they kind of leave steps out. What's the only thing I can multiply something by and not change it? What can I multiply it by? 1. So what they're doing is they're taking this thing under here and they're multiplying by 1. That doesn't change anything by the identity property of multiplication. The way they write 1 is just kind of a weird way. They write it as delta x squared over itself. I mean, anything over itself except 0 over 0 is indeed what? 1. Then what they do is, think about it. If you have a number times a fraction, a whole number times a fraction, couldn't you instead slide this denominator under that one and leave that numerator? Wouldn't that give you the exact same numerical answer? So that's what they do. They just slide this one underneath there, and then they still got this one on the top. Well, now, what is anything divided by itself? Again, we've said that anything divided by itself besides 0 over 0 is what? 1. And then there's their delta y squared over their delta x squared. Now, there's also a theorem in algebra that basically says this. If you've got the square root of 2 numbers multiplied, that's the square root of the first one times the square root of the second. Think about it. Isn't 36 4 times 9? Well, is that the square root of 4 times the square root of 9? I wonder, what's the square root of 4? 2. What's the square root of 9? 3. And 2 times 3 is indeed what? 6. Is the square root of 36 6? Now, in math, is that legal algebraically? Try it with numbers. Is this true? Is the square root of a plus b the square root of a plus the square root of b? Well, let's try that. Square root of 9. Isn't 9 4 plus 5? Well, is that the square root of 4 plus the square root of 5? See, that one doesn't work, does it? Because I know what's this answer? This answer 3. Well, that answer's 2, but that answer's not 1. So if you get confused about something, try it with numbers. If it works with the numbers, it works with variables. So, they don't make a big deal about it. That's what they do here. They break this up into the square root of this one times the square root of that one. Well, what's the square root of something squared? Just what? Just that thing back, isn't it? So they've got this 1 plus delta y over delta x squared. Now, think about it. What happens when you have more and more and more of these segments? Wouldn't this approximation get better and better to being the real thing? So that's why all of a sudden they decided to take the limit as their number of segments increases without a bound. Now, the trick is they kind of remind you of something that you had supposedly in Cal 1, which is called that mean value theorem. And that mean value theorem, I went ahead and wrote it down. It's on page 216. It basically says this in your book. Now that was the one in Cal 1 where they would do something like this. They would really want this tangent right here. So they would basically talk about somewhere the tangent of this secant is going to be the same thing. So if I've got an AB here, so I've got a point here and a point here. So the slope of this one would be, you know, f of B minus f of A over B minus A. If that's A, f of A, and that's B, f of B, then the change in Y over the change in X, wouldn't that be the slope of the tangent line? And so in Cal 1, they said there's got to be some point between A and B, call it C, where the slope of that line is parallel to that line. So instead of using this one, you could use that one instead. So that's all they do. They don't really make a big deal about it. They just change this delta y over delta x to this derivative by that mean value theorem. And then this should look real familiar to you. This is your definition of the definite integral. And then you learned about differentials in Cal 1, that delta x and dx are the same. So that's why this ends up being your formula. But for you, all you've got to do is just do what to this formula. Just memorize it. Everybody okay? All right, so look at the one we're looking at. All right, so on number 7, they give me my curve. They even draw it for me. I've got y equals 2/3, and I've got x squared plus 1 to the, what is it, 3/2, is that right? Okay, now, and I'll look at the interval. What's their x value? Looks like they're going from 0 to what on my picture? 1, all right. So I'm going from 0 to 1. So I've got to have the square root of 1 plus. Now what have I got to go do to fill this in? I've got to take the what of this one? The derivative. All right, you help me. All right, what's going to happen to that 3/2? It's going to come down front, isn't it? But there was already a what there? A 2/3. My expression stays the same. What do you do with derivatives though? You go up or down? You go down with the power. So what's 3/2 minus 1 going to give me? 1/2. Now, if you stopped here, what'd you forget to do from Cal 1? What's that extended power rule say you have to do now? Take the derivative of the inside. So what's the derivative of that inside going to give me? 2x. So what's this 2/3 times this 3/2 going to do? Just goes away, doesn't it? So I get x squared plus 1 to the 1/2 times a what? 2x. But now I've got another problem. It's not just the derivative, it's the derivative what? Squared. So if I need the derivative squared, I'm going to have to take this thing, and I'm going to have to do what to it? I'm going to have to square it. Now again, we're back to 7th grade math and 8th grade math. If you have a 2 times a 3 squared, isn't that 6 squared, which is 36? Is that the same thing as 2 squared times 3 squared, 4 times 9? Yeah. So I've got to square this one and I got to square what? That one. So what's happening when I square this 1/2? What's going to happen to that 1/2 and that 2? They're going to go away. That's going to leave me an x squared what? Plus 1. But then I got to square this 2x. So what happens when you square a 2x? What do you get? 4x squared. All right. So can I multiply that out? So that's going to get me a 4x to the what? 4 plus a what? 4x squared. Everybody okay? Now this is one where I kind of warned you. We're going to do surface area today, and it's actually easier to me than our plan. all right? He's got very few problems that you know how to integrate. And the key here is arranging this differently. Community property of addition. 4x to the fourth plus 4x squared plus 1. See, what I've got to recognize is that's a perfect square. What do you square to get 4x squared? 2x. What? Square. What do you square to get 1? 1. Now double check. 2x squared is 4x squared. How do you get the middle term? Don't you say this one times this one and then you double it? So 2x squared times 1 is 2x squared. Doubled is indeed what? 4x squared. And then when you square 1, you get 1. Now, why is that nice? Because when you take the square root of something squared, what happens? That's what I'm saying. So there are very few that he can kind of do with you. So I'm integrating from 0 to 1, and I've got 2x squared plus 1 dx. So what happens when I integrate 2x squared? I'm going to get 2. What happens with x squared? I get x what? Cubed over 3. What happens when you integrate 1? You get a what? An x. And I'm going from 0 to what? 1. So when I plug a 1 in there, 1 cubed is 1. So what am I going to get here? A 2 what? 2/3 plus a what? A 1. What's going to happen when I plug 0 in both places? It just goes away. And what's 2/3 plus 1 going to get? 5/3. Are we okay? Or is there another one somebody needs to see set up or anything? Are we okay? Now, let's see, what's one of the ones that you had asked me about? Because I need to make sure that I go over something because I'm not sure I made it clear. One of those volume ones that you asked me about. Do you remember? Which one was it?
Page 470, 23, and 25.
All right, let me show you something on like, it doesn't really matter which one, like 23. All right, I want to show y'all something to make sure that I make this clear, because I don't think I did last time. All right, look at 23. All right. All right, one of my graphs is y equals 2x minus x squared. Okay. And then another one of mine is y equals 0. And what am I rotating around? I'm rotating around, is it x equals 4? Okay. Now, on your test, it's going to be next week, all right? Even if you're sure you know what the graph looks like, you've got your graph and take advantage of it. Even without my graph, where I know that's parabola, and that parabola turns down. Okay, but I'm going to double check it because I've got permission to do that. So I've got my 2x minus my x squared, and I graph that and double check it. And sure enough, I was right. All right, that's a parabola that turns down. All right, now what's y equals 0? Just the what? X-axis. And I'm rotating around x equals what? 4. All right, so I need to know what these points are. Now, I'm not going to trust necessarily the graph. I know what it looks like it goes through, but I'm going to double check it. What does y equal on both of these points? Y equals what? 0. Okay. So if y equals 0, I can set 0 equal to that 2x minus x squared. Now that's a quadratic equation. Don't we factor quadratic equations? So what can I pull out? An x. What's that going to leave me right here? A 2 minus a x. So either this first thing is 0 or this second thing is 0. Well, either x is 0 or x is what? 2. So it looked like 0 and 2, but you know, if it was 0.0013, I wouldn't be able to tell that with the naked eye. So I'm going to algebraically double check. Now, the reason I didn't know that is I needed to know where x equals 4 was. So it's apparently past this somewhere. All right, so out here I've got x equals 4. Now, so my shading is right here. Now, I'm not going to tell you which way to work it, okay? But suppose I decided that I wanted, and I'll show you why in a minute. Suppose I decided that I wanted to draw my rectangle vertical. Now, if I draw that rectangle vertical, is it going to be dx or dy? It's going to be dx. So these have to be x numbers. So hence, I really needed to know what those x numbers were. So what are the x numbers on my shading running from? 0 to what? To 2. Now, if I'm flipping around this blue vertical line, and that's my rectangle, are they parallel or perpendicular?
Parallel.
They're parallel, so I have to use what? Shell. What goes in front on shell? 2 pi. And again, I need a p and a what? An h. Now, here's the part I think I made super clear. So let's see if I can fix it. P is from the axis of rotation to the middle of that rectangle. So do we agree that this is P? Now, that again is a horizontal distance. So it's got to be x on the right minus x on the what? Left. Now, same thing. If you wanted to graph the point 2, 0, would you start here and go 2, or would you start here and go 2? Where do you always measure from? From the what? From the origins. Everybody with me? So, from here to there is just an x coordinates. Everybody with me? But from here to here, see, if x on the right, I need this distance, so I need this x. So what's this x value? This x value is what? 4. Now, this right here is just an x value. Is everybody with me? So if all the way over, do a different color. If all the way over is 4, and this little part is x, what is p? P is 4 what? Minus x. But just make sure when you're getting just an x or just a y, you have to be starting at the axis, at the origin. Now, what about h? Well, h is the height of the rectangle. Now again, if it's a vertical thing, it's got to be y on the top minus what? Y on the bottom. All right, so what is your y on the top? Well, again, I can't just, I'm coming from the origin, why can't I just put y? Because it says d what? Dx. So on that green one, what is my y? My y is 2x minus what? X squared. But what's the y on the bottom? Well, the y on the red is just what? 0. So does everybody understand that what you're integrating is just 4 minus x times 2x minus x squared? And can't you just multiply that thing out and have 4 little power rules? Is everybody okay? Now, you say, well, I don't want to do that. I don't like shell. Okay. If you don't like shell, then you're going to have to draw your rectangle this way. Which means you got to have d what? dy, right? All right, you've already got a problem. Already from the get-go. You know the smallest y value. What's the smallest y value? But now you got to know what the peak of that parabola is. You got to go find the vertex on that parabola, which means you got to go start completing the square on this thing. See, we're already in trouble. Is everybody with me? Then, even if you can find this number right here, now you're perpendicular. So you'd have to use disc or washer. Since there's a gap, you'd have to use what? Washer. Well, there's a pi in the front. Don't you have 2 radii? Well, your first R has to be from the axis of rotation to the outside of the shading. Okay, what's your X on the right? No problem, it's what? 4. What's that X value on that green? Are you gonna be able to solve that thing for X? See, this is what I mean by sometimes you're gonna be forced, there's only one method that you can use. It's not that I'm gonna tell you to use it, it's just you won't know what to put here. You say, well, I'm gonna solve that for X, okay? How you gonna do that? That's a nasty algebra. Because even if you factored an X out, wouldn't that leave you 2 minus X? Well, you can't have X is Y over 2 minus X. Now, you still got a mix. You see what I'm saying? You can't make it say X equals and just have Y's on the other side. So that's what I mean by, I'm not going to tell you which way to set it up. You're going to decide which way you're going to set it up. But there are going to be probably 1 or 2 where you're not going to know how to set the other one up. So you're going to be forced to go to the other one. Okay? But does that make sense? Why sometimes this P is just X and sometimes this P is just Y. But if you're flipping around something besides an axis, it's going to be a number plus or minus that X, or a number plus or minus that Y. Okay, so if you have trouble, just like I said, let me know and we'll work on it. All right, so does everybody understand then, theoretically, how to do disc, washer, and shell? All right, except for the arithmetic, does everybody understand how to do arc length? Now, let me show you surface area. Here's why surface area to me is easier than arc length. All right, now, rather than taking the time to derive that one, it's similar to the derivation over here of this arc length. So you can read it in your book. Here's why surface area is easier. Your surface area formula is almost like your arc length formula. Now remember, what is arc length? Arc length, you're integrating from A to B, and you got 1 plus the derivative what? Squared. That's arc length. All right, on page 479 in your books, they give you surface area. Now, they kind of do capital S, and they do this one little s, but it's hard for me to tell the difference between my little s and my capital S, so I'm just going to put SA for surface area. Here's one thing, it's almost just like this one. There is the same root with some extra stuff. So the same root that's on surface, on arc length is on surface area, and the reason is if I rotated that thing around the x-axis, surface area is like I'm just painting the outside of that veil. Is everybody with me? But it's got to do with this length. It comes from basically the area of a frustum. A frustum, if you remember from geometry, is like somebody took a cone and chopped off the tip. Okay? So they kind of show you where it comes from, but here's the difference. The difference is there's a radius out here. So it matters how far this is away, because I mean, the further it is, the bigger the thing's going to be, so the surface area is going to be bigger. Is everybody with me? See, it doesn't matter where, if you're just doing arc length, it doesn't matter where you put it. The distance from here to here is going to be the same whether you move it up or move it down or move it over or move it this way. But if you start rotating around an axis, how far that thing is away from that axis does change the surface area. And then in front, there's a 2 pi. Now, let me tell you one of your challenges then for your test next week. All right. Your test next week is basically going to cover 4 things. It's going to cover area between curves. All right. It's going to cover volume. It's going to cover arc length. And it's going to cover surface area. Now, one of the mistakes somebody will make is what's in front of the integration. Because sometimes there's nothing, sometimes there's 1 pi, and sometimes there's what? 2 pi. So you need to get straight in your head when it's what? Now, what's in front on area between curves? What? Nothing. What else has nothing in front of it? Arc length. So the way that I used to remember is both of those are 2-dimensional. See, area between curve, are you rotating around anything? What? No. On arc length, are you rotating around anything on arc length? Again, what? No. So when you're not rotating around anything, there's nothing in front of that integration. So that's the way I remember it. I don't care how you remember it, you can just flat memorize it. All right? When is there a single pi in front of something? What? What's got pi in front of it? Disc or washer. All right? What's got a 2 pi in front of it?
Surface area.
They both start with an S. You see what I'm saying? Any memory trick you can do, but shell and surface area both have a 2 pi in front of it. So one thing you want to do is keep straight when you don't have anything in front, when you got a 1 pi in front, and when you got a 2 pi in front. All right? With area between curves, it starts out the same. You know, you're going to have some curve and some other curve, and I'm going to ask you to find the area between the two. You're not rotating around anything. But you are going to draw and shade and then draw yourself a rectangle. Either vertical again or what? Horizontal. And I'm not going to tell you which way to draw it. Now, sometimes it may even be that you may have to do more than one integration. You know, if I start going, you know, like up, down, up, and I want the distance, I want the area between the pink curve and the x-axis, between pink and blue would be here, but it would also be what? There. So, you know, I've got to figure out, I might have to do, if I want to do a vertical rectangle here and a vertical rectangle here, I'm going to have two different integrations because what's on top and what's on bottom is going to change. But vertical length still going to be y on the top minus what? Y on the bottom. A horizontal rectangle still going to be x on the right minus what? X on the left. All right? If you want to do volume, again, it doesn't matter whether you draw vertical or horizontal, but on either one of these, as soon as you draw vertical, is it dx or dy? Dx. When you draw a horizontal rectangle, it's dy. Dy. So you've got to decide. Then on volume, you look and see whether your rectangle is parallel to what you're flipping around or perpendicular. If it's parallel, you have to use what? What do you have to use if they're parallel to each other? The rectangle and the axis of rotation. Shell. You have choice. Now, if that's vertical, it's dx. If it's horizontal, it's dy. But the dx, dy's got nothing to do with the method. That's simply the orientation of the rectangle. Now, if it's perpendicular, it's either disc or washer. How do I decide between disc and washer? Gap or no gap? Okay. Now, if it's arc length, it's just this formula, which means you got to take the derivative and then pray to the Holy Spirit that this is something you know how to integrate. Okay? Because those integrations get to be gnarly, and here's why surface area is easier. See, don't you have something to a 1/2 power all the time? Well, the reason he keeps getting perfect squares is because when he takes the square root of something squared, it goes away. Is everybody with me? Because if he doesn't have the square root of something squared, he's going to have some junk to a 1/2 power. Well, go back in your mind to when we were doing harder integrations. Remember that extended power rule. When you have something to a power, next to it, don't you need the derivative of the inside if you don't want to use U substitution? Well, see, now you got something out here to work with. You're gonna have something outside that might help you get the derivative of this inside piece. All right, now, just like before, this radius, this R is a radius. And it's the distance from the axis of rotation to the curve. Now, there's no shading on arc length, is there? There isn't, right? And there's no shading on surface area. So let's kind of go do one. All right, on page 480, here's what they tell us. All right. It says, find the area of the surface formed by revolving the graph of y equals x cubed on the interval from 0 to 1, and they're going to flip it around the x-axis. All right, rotate y equals x cubed from 0 to 1 around the x-axis. Okay. Now, what does y equals x cubed look like? We've already talked about it this morning. What does it look like? It's just a what? An S curve. But do I want the whole S curve? I just want it between 0 and 1. 1. So I'm going to kind of exaggerate it. Okay. So, you know, there's 0, 0. Here's 1, 1. You know, and I'm wanting basically this. That's my arc length. Now, does everybody understand that if that's my arc length, if I rotate around this x-axis, do you see I get something kind of like the end of a trumpet? I get a little bell. And if I wanted to paint the outside of that three-dimensional shape, so it's in your book drawn on page 480, and they do a much better job of drawing than me. But is there any shading? No, because there's only one curve. Is everybody with me? Now, what did I say R was? R is the distance from what? The axis of rotation to the what? To the curve. Now, what am I flipping around? I'm flipping around the x-axis, and here's my curve. So that's my radius. Now, you help me out. Look at why this integration is so much nicer. I've got a 2 pi. Now, most of the time, you're going to do dx's unless the formula basically says something like x equals y cubed. Is everybody with me? So most of the time, y'all are going to do dx's. So sure enough, what are my x's running from? From what? 0 to 1. Why did I stick a 2 pi in front of it? Because that's part of the formula. Now, what's this radius? Well, again, is this a vertical length or horizontal length for R? It's vertical. So if it's vertical, it's what? Y on the top minus what? Y on the bottom. Now again, why am I not going to put Y? Because it says what? Dx. So what is the Y on that red curve right there? It's what? X cubed. Minus, what's my Y on the bottom? It's just what? 0. So does everybody understand that that's my R? And I've got the square root. I've got 1 plus. Now what have I got to go over to the side and do? Take the what? The derivative. All right, you help me. If Y is x cubed, what's the derivative?
3x.
Good, 3x squared. There's count 1. But it's not just the derivative, it's the derivative what? Squared. So if I take that derivative and I square it, I've got to take this 3x squared and square it. So what do I end up getting? 9x to the 4. So I've got 1 plus 9x to the 4th. Now, look at why this integration is so much easier. I've got 2 pi. I'm running from 0 to 1. Now we got to go back in our minds to the integrations that were a little more challenging. What's the first thing you learned to do with roots way back in January? What do roots always get changed to when you're integrating? You got to change the power. So that's going to be 1 plus 9x to the 4th to what power? The 1/2. Now I'm going to change the order a minute just to make you see it a little bit better. So I've got 1 plus 9x to the 4th to the 1/2, and I've still got this x what? Cubed. So that extended power rule that we went over said if you've got something to a power, what do you have to have sitting right next to it? The derivative of what? The inside. Okay, what's the derivative of that inside? 36x what? What have you got? You got the x cubed. What's the only thing you're missing? Well, that's easy. I can multiply by 36 if I also multiply by what? 1 over 36. There we go. Now I'm going to kind of go up here because I'm out of room. So what's 2 pi over 36 simplify into? Pi over what? 18. So what happens when you're integrating? You got something to a power and you got the derivative next to it. Don't you have your original? Okay, remind me what I do when I'm integrating to my power. When you're integrating, what happens to your power? You go up or down? Up by how much? 1. So when I add 1 to 1/2, what am I going to get? 3/2. Now I've got to divide by that 3/2. That's the same thing as multiplying by what? 2/3. And again, I'm running from what? 0 to what? 1 to 1. All right. What does all this junk in front of this parenthesis simplify into? Pi over what? 27. Okay. Now, I've got 1 plus 9x to the 4th, and again, I'm running from 0 to 1. Is everybody with me? All right, but that whole thing is to what power? 3/2. Now we got to get good with roots and fractions. So I've got pi over 27. Let's plug in the 1. What's 1 to the 4th? 1. What's 9 times 1? 9 plus 1 more. So I've got 10 to the 3/2. Everybody okay with that one? Minus. Now, when I plug in 0, does the whole thing get wiped out? Be careful. No, so be careful, it doesn't. Now, this part gets wiped out. But what's left? 1. Now, what's 1 to any power? So 1 to 3/2 is going to be what? 1. All right, let me kind of erase this and get a little more room. Now, I want an exact answer, because like I said, in the real world, usually you're working in teams. I don't want somebody. So I've got 10 to the 2/3 minus 1. And I've got pi over 27. Now, I'm going to see if I can simplify that any. What does 10 to the 2/3 mean? Well, that's 10 to the 1/3 what? Squared, isn't it?
3/2, right?
Oh, thank you, 3/2. So that's 10 to the 1/2, then what? Cubed. So what's 10 to the 1/2 just a way of saying? Square root of 10. So what's the square root of 10 cubed mean? How many square roots of 10s do you have? 3. What happens every time you get a pair? So what is this a strange way of saying? That's just what? 10, the square root of what? 10, isn't it? Because the square root of 10 times the square root of 10 would be 10, but I've still got a square root of 10 left. Now, I can't really make that look any better. That's just a gnarly answer. You can leave it like this, or you can leave it like that. Now, if somebody wants a decimal approximation, I'm confident they can take their calculator and get a decimal approximation. But that's what I mean by, to me, the surface areas are easier than the arc length because I've got this radius out here. And a lot of times this radius is going to help me have something outside so I can get the derivative of that inside. Okay. So that's kind of where your test material is going to stop. Now, let's set one more up just to make sure that we understand. Okay, let's see what we're going to do now. All right, look at this other example real quick. I'm gonna leave that formula right now. On example 7, they're gonna rotate y equals x squared on the interval from 0 to the square root of 2. This time they're gonna go around the y-axis. Okay. No problem. What does y equals x squared look like? It looks like a what? A parabola. But do I want the whole parabola? I want from x being 0 to x being the square root of 2. So this is 0, 0. This would be the square root of 2 comma what? How would you get the y coordinate? Would you give me what? 2. All right, but this time I'm rotating around which axis? The y-axis. So draw your R on your picture, and let's double check and make sure you drew it right. So if I told you to draw your R, okay. Now, does everybody understand where does R go from? From the axis of rotation, what? To the curve? So, do we understand that that would be R? All right. Now, if you decide you want to do dx, then these have to be x numbers. What would the x numbers be running from? 0 to the square root of 2. And you're like, oh. Okay. Now, this time it's not a vertical length, it's a horizontal length. What's a horizontal length? X on the right minus what? X on the left. So X on the right. Now, we're not going from the origin over. So can I just call it X? Minus, what's the X on the left going to be? So that's my radius. Now, why don't you want to do X on the right? Why don't you want to say, well, X on the red curve, X would be the square root of Y. Why don't you want to put the square root of Y right there? Because it said what? The X. So it's like P. In other words, I'm just going from the origin over, so the X on that red curve can just be X. And I've got the square root of 1 plus. Now, what have I got to do over here? I've got to take the what? The derivative. All right, y is x squared. What's the derivative going to get me? 2x. But what have I got to do to that derivative? I've got to square it. So what happens when you square 2x? What do you get? 4x squared. Now, again, I'm gonna reorder some things just to make it a little clearer. What can I change this root to? What's the first one we want to do when we're integrating roots? We change them to what? To powers. All right, so that's gonna be 1 plus 4x squared to what power? 1/2. Now, what do I still have out here? This what? And there's still an x. X minus 0 is just what? X. So don't you have something to a power? So in order to integrate, don't you need the derivative of the inside? But see, what's the derivative of that inside? 8x. Don't you have the x? So what's the only thing you're missing? Well, you can multiply by 8 if out here you multiply by what? 1/8. So what is this stuff in front of this integration clean up into? What's 2 pi over 8 simplify to? Pi over 4. Now I'm integrating something to a power and I got the derivative of the inside next to it. Remember what we said, that's your original 1 plus 4x squared. What are you gonna do to that power when you're integrating? Don't we add 1? So what's that gonna make it of what? 3/2. Okay, what's the same thing as dividing by 3/2 multiplying by 2/3? And again, I'm going from 0 to what? Square root of 2. All right, what's the stuff in front of the parenthesis clean up into? All right, pi over what, 6? Okay. All right, so let's put that square root of 2 in there. All right, what's the square root of 2 squared? 2 times 4. 8 plus 1, 9. So I've got 9 to the 3/2 minus. When I plug 0 in there, does it wipe it out? It doesn't, does it? It wipes out the 4x squared, but what's still left? A 1 to the 3/2. Now, what's 1 to the 3/2 just what? 1. So I've got a pi over 6. Now, 9 to the 3/2. Isn't that the same thing as 9 to the 1/2 cubed? What's 9 to the 1/2 really mean? The what? Square root of 9. So what's the square root of 9? 3. And what's 3 cubed? 27. But I still got minus 1, don't I? All right, so what's that gonna give me? 26. So what's 26 pi over 6 simplify into?
13 pi over 3.
Yep. And again, if you want a decimal approximation, you can get it. So that's where your test materials stop, so it's a week from today. All right, now part of your homework gonna be a course where? On Moodle, so I'm gonna give you some surface area ones to do. But I'm also gonna give you some out of the review kind of mixed up to do some area, some volume, arc length, and surface area. And so on your test, some of them will be everything from start to finish. Some will be just draw them and set them up and stop, so that you can have more problems. Otherwise, there'll be like 4 problems on your test. Okay, because sometimes they take a while. Sometimes it may be you draw it, set it up, then I give you the choice of finishing it by hand or getting me a decimal approximation off the calculator. So you probably need to practice that a little bit. Everybody, we talked about it last time. All right, I will see y'all next time. Come see me if you need some help.